Hello everyone, my name is Tianbo from University of Science and Technology of China and the Institute of Computing Technology, Chinese Academy of Science. In this talk, I will present Cambricon-SR, an accelerator for neural scene representation with sparse encoding table. Here is the outline of this talk. To begin with, I will talk about background of the neural scene representation. Neural scene representation, or NSR for short, has emerged as a promising technique for reconstructing realistic 3D scenes with high quality. It takes multiple photos taken from different camera positions as the input and outputs a model containing learned parameters that can represent a 3D scene. The NSR can reduce the camera cost from the expensive laser camera to cheap color camera. Thus, NSR can boost productivity for many applications such as autonomous driving, embodied intelligence, and VR, and AR and VR. However, the insufficient modeling speed restricts the application of NSR. For example, in autonomous driving, currently NSR can only be used for modeling the environment offline for data generation and driving simulation, but cannot be used for modeling the changing environment online. A prior Cambricon-R can support real-time NSR modeling, but at the cost of the modeling quality. Specifically, Cambricon-R can train only around 250 iterations under the constraint of the real-time constraints, which is insufficient for real-world large-scale scenes. As we can see from the images, the detail is quite blurry. Objects like the book and the ball can hardly be recognized. To improve the NSR performance, I will first briefly introduce the processing of the NSR. The processing of NSR can be divided into 5 stages: sampling, encoding, MLP, loss, and premise updating. Among these stages, the encoding stage is often considered as a performance bottleneck. The encoding stage performs lookup in the encoding tables. The main challenge in the encoding stage is the large number of the fine-grained irregular memory accesses. On GPU, around 30% of the total runtime are spent on the encoding stage, with around half of the total memory accesses. In this work, in order to improve the encoding performance, we propose ST-NSR algorithm, which is an NSR training algorithm based on sparse encoding table. After that, we further propose an hardware architecture called Cambricon-SR to take full advantage of the ST-NSR algorithm. Cambricon-SR includes 2 main techniques. First, we propose sparse update unit to eliminate redundant accesses to the dense table during the updating of the sparse table. Second, we propose sparse index unit to filter out invalid table accesses with minimal area overhead. To reduce frequent accesses to the encoding table, we propose a sparsity-aware algorithm called ST-NSR. The core idea of ST-NSR is to access a pruned version of the encoding table. We refer to this table as the sparse table, since many entries in the sparse table is pruned into 0. Accesses to those entries can be eliminated. However, the sparse table cannot be directly updated via gradient accumulation because the pruned entries don't exist in the sparse table and cannot be updated. In order to address this issue, we retain the unpruned encoding table for parameter updating, which we call the dense table. Gradients computed through backpropagation are directly applied to the dense table. After that, a new sparse table is regenerated from the dense table using the sparsity threshold. As a result, ST-NSR algorithm can achieve over 80% sparsity with less than 0.5 PSNR drop. To fully take advantage of the ST-NSR algorithm, we propose a hardware architecture called Cambricon-SR. The top figure shows the overall data flow of Cambricon-SR. It mainly includes two stages, the forward and backward stage, and the update stage. During the forward and backward stage, sampling, encoding, and MLP are executed in a fine-grained pipeline manner. During the update stage, trainable parameters including MLP weights and table entries are updated in sequence. And the bottom figure shows the overall architecture of Cambricon-SR. Cambricon-SR mainly includes a sampling module, an encoding module, an MLP module, and an update module for, for different stages of NSR. To reduce off-chip memory accesses, Cambricon-SR stores most of the data on chip, except the dense table, due to the large size and the regular access pattern of the dense table. We find that update of the sparse table becomes a performance bottleneck. Updating the sparse table involves reading the entire dense table from off-chip memory and comparing it with the threshold, accounting for 59% of the total runtime. However, only a few entries in the dense table are actually used, which means that there is a great number of redundant accesses. As shown in the example in the bottom figure, only one entry is used during updating, but the whole dense table is read. To address this issue, we first analyze the sparsity changes between adjacent iterations. We observed that no more than 0.8% of entries change their sparsity status between adjacent iterations. And for the majority of entries whose sparsity remains unchanged, their update process can be merged with the dense table updates, thus avoiding the redundant accesses. Based on this observation, we proposed the sparse update strategy and the corresponding hardware support. Specifically, for entries with unchanged sparsity, they can be directly updated during the update of the dense table, as shown in the blue arrows in the figure. For minimum entries with changed sparsity, they are temporarily stored in two queues, as shown in the right red block. QA is for entries changing from unpruned to pruned, and QB is from pruned to unpruned. At each step, one element is read from each of two queues simultaneously. After that, the pruned entry is removed from the sparse table, and the unpruned entry is inserted into the vacancy. This mechanism avoids overhead of extensive data movements. According to our evaluation, through the sparse update unit, the time for parameters updates can be reduced by 5.28 times. Another issue is the filtering of invalid memory accesses. To filter out invalid accesses toward pruned entries, we use a bitmap that indicates the sparsity of each entry to determine the validity of the memory accesses. In order to fully utilize the throughput of the encoding table access, around 2,000 irregular bits are read from the bitmap in each cycle, which is challenging due to the high throughput requirement and the irregular access pattern. The straightforward solution requires the bitmap SRAM contain approximately 2,000 banks and a 2,000 to 2,000 crossbar. However, a crossbar of this scale is too large to be feasible. Even if such a crossbar could be implemented, irregular memory accesses would cause bank conflicts, reducing throughput to only 17% of the peak throughput. To address this issue, we observed that the root cause of bank conflicts lies in the irregular memory accesses. Therefore, we propose to perform sequential access on the bitmap to avoid this problem. In our approach, memory access requests cannot immediately get the result of validity and must instead be temporarily stored in a buffer. Meanwhile, the bitmap is accessed sequentially and and the addresses are compared with the requests in the buffer to determine the validity of accesses. The validity memory accesses are stored in the output queue for further processing, while the invalid memory accesses are filtered out. However, this solution introduces a significant matching latency, and the large latency brings a huge buffer capacity requirement. As a result, the total area overhead reaches around 400 square millimeters, which is unacceptable for practical implementation. In order to reduce the latency, we perform multiple sequential accesses simultaneously and adopt a two-level grouping approach to increase the parallelism. Specifically, we first group memory access requests based on their high address bits, where each group only needs to access the corresponding range of the bitmap. Meanwhile, different banks of the bitmap perform sequential accesses in parallel. We locate the nearest access address to each request and only compare that request with the address, thus significantly reducing the number of comparators. Finally, according to our evaluation, by filtering out invalid memory accesses, the sparse index unit can achieve 7.54 times performance improvement in the encoding stage with only 8.6% additional area of the total chip. Next, I will introduce the evaluation result of our architecture. We choose NVIDIA A100 GPU and Cambricon-R as the baseline. According to our evaluation, Cambricon-SR can achieve 1,259 times speed up over GPU and 4.12 times speed up over Cambricon-R. The primary reason behind our significant speed up over GPU is that we store the vast majority of intermediate data on chip, thereby eliminating approximately 99.8% of the off-chip memory accesses. Compared with Cambricon-R, our performance improvement mainly comes from the reduced number of accesses to the encoding table. We also evaluate energy consumption, and we find that Cambricon-SR reduced energy consumption by around 1,139 times over GPU and 2.98 times over Cambricon-R. The breakdown result shows that around 50% of the total energy is spent in the memory accesses to the encoding table, and the sparse index unit only consumed around 16.77% of the total energy. Due to the performance improvement, Cambricon-SR can achieve a better performance quality trade-off. It means that more training iteration and better quality can be achieved at the same training time, and less training time is required under the same quality requirement. As a result, Cambricon-SR can achieve PSNR of more than 25 within 0.1 second of training on several real-world room-scale scenes. And here is the summary of this talk. First, we propose STNSR algorithm to reduce the number of valid encoding table accesses by pruning the encoding table. Second, we propose sparse update unit to eliminate redundant accesses to dense table during updating the sparse table. Finally, we propose sparse index unit to filter out invalid memory accesses to prune entry with minimum area overhead. According to our evaluation, Cambricon-SR can achieve about 4.12 times speed up and 2.98 times energy saving over the SOTA-NSR training accelerator. Thus, Cambricon-SR can improve the performance quality trade-off. Okay, that's all of my presentation. Thanks for your listening. I'm happy to take questions.